Hello, good morning. Sorry about the delay. I forgot my this bag, so I had to get back to my office to get them. So, so we were talking about today is Thursday, March 16. Um, we were last time we talked about how to find the inverse Laplace transforms of several functions in the S domain, and finding inverse Laplace transform means we're transforming from an S domain into a time domain. On the other hand, if you take a Laplace transform of some function in the time domain, we're transforming it into an S domain. So we talked about a couple of cases where the first case, the poles are. In the first case, all the poles are distinct. Okay, when all the poles are distinct, we can do the decomposition. We can do the partial fraction decomposition of the function that we want to take a inverse Laplace transform into terms. Okay, the number of terms is determined by the number of poles that are distinct. For example, here, P1, P2 through Pn are all distinct, so there are n terms here. The coefficients K1 through Kn are generally could be a real number or complex numbers, and the coefficients Ki, okay, Ki being from 1 through n, is determined by multiplying the polynomial Hs by S minus Pi, and once you get the result, you plug in S equal to Pi, and the result will be the coefficients Ki. Okay, we have to do this for all of the n terms here to get all of the k's. And once we've got all of the k's, then we can take the inverse Laplace transform of each of the terms. And we know that if we take the inverse Laplace transform of a function of this term, then the time domain flip will be the exponential function with Pi being the coefficient in the exponent term here. And don't forget about the unit step function, because it starts at time 0. All of them start at time 0. And then we add them together using the linearity of the Laplace transform, and we get the inverse Laplace transform of H. So this is the simplest case. This is the easiest case. Now the second case was when some of the poles are repeated. For example, here if we have the function h of s written like this. By the way, z's, zi, z1 through zm are called zeros of the function, and k is a coefficient. Usually k is a real number. And in this case, P1 is the one pole that is distinct from the rest, while P2 is repeated r times. So what I mean by repeated poles is that in this case there are r plus 1 poles, and the first pole is P1 and P2 and there are r P2s. Okay, P2s there are values. I mean, the P2s are repeated r times. It's repeated r times. And when there are repeated poles, then we have to write down the terms associated with the repeated poles have to be broken down into r terms like this. So if you look at the denominator, you see the first term is s minus P2, which is the P2 is the repeated pole, and the second term you cannot just write down s minus P2, because if you just write it down like this, it will be the same as the first term, and it will get you nowhere. So what you have to do is you have to square it, and the third term you cube it. Okay, you take the third square of it, and then for the last term, right? You take it to the odd power and you add them together. While the first term is the one associated with a pole that is distinct from the rest. So this is the easiest one. Now, to find you see there, because there are r plus one terms, r plus one poles, so there are also r plus one terms here. So the number of terms here have to be the same as the number of poles here, right? And then you can find K1, which is the associated with the distinct pole. And K1 is easy because you just use the same formula that we did in the previous case by multiplying S minus P1 to HS and then plug in S equal to P1 to the result, and then we're going to get the coefficients K1. And the last term is also easy. You just multiply all of this by S minus P2 to the R, and then once you do that, you plug in S equal to P2, then all of the terms here will be cancelled out, and you're gonna get the coefficient K R plus 1 back. So that's how we got K R plus 1. But for K2 through KR, right? The best way to do is to plug in K1 and KR plus 1 into the right hand side of this equation, and then do the algebra and then compare the coefficients. Once we compare the coefficients, we will be able to get the rest of the case. For example, here in this case, HS is decomposed into 3 terms here because there are 3 poles. Now the first and the last terms, the K's are 1 and 2, while the middle one is determined by comparing the coefficient here. Okay, because we know that this numerator has to be equal to S. So we know that K2 minus 1 has to be equal to 0, while 3K2 minus 2 has to be equal to 1, and 2K2 minus 2 has to be equal to 0 again. So we compare them and we solve the equations. We can see that K2 in this case is equal to 1, and then we have 1 here. Now, once we have all the terms here, we can take the inverse of the Laplace transform by recognizing that this term corresponds to e to the negative t ut. And this term corresponds to e to the negative 2t ut. And the last term, for the last term, we have to use this formula here. Okay, in this case, n is equal to 1 because we have the second power here, so n is equal to 1. Right, so when we plug in n equal to 1 here, we're going to get t e to the negative 2t. Okay, t e to the negative 2t there. And then we have ht back. Now that was for repeated poles. And in the last case, in the third case, we want to focus on, we want to look at the case where some of the poles are complex numbers. Now, when there is a pole that is a complex number, there has to be another pole that is also a complex number, and these two poles have to be a conjugate pair. You know, because we are assuming that the coefficients of H are constant, so poles have to come in conjugate pairs. Otherwise, the coefficients of H would not be a real number. For example, here, let's look at this case. Hs is equal to s plus 1 over s times s squared plus 4s plus 29. We want to find the inverse Laplace transform of this particular function. Now, this case is easy, okay? This term is easy because the pole associated with this term is 0. So we know right away that here we have P1 equal to 0. Now, we need to consider this term, right? Consider this term. A squared plus 4s plus 29. Okay, we do the decomposition. We find that it is equal to s plus 2, right? S plus 2 squared minus 2 squared plus 29. Okay, and this is equal to s plus 2 squared plus 5 squared. Okay, s plus 2 squared plus 5 squared. And then we do the perfect squared, which is s plus 2 squared minus j5 squared. Okay, j being the imaginary constant. And so we have two terms multiplied together. The first being s plus 2 minus j5, and the second is s plus 2 plus j5. Okay, and so from here we see that there are two poles. So another two poles are P2 equal to minus 2 plus j5 and P3 equal to minus 2 minus j5. So at this point, we know that there are three poles. Okay, the first being 0. The first is at 0. The second, you see, the second pole and third pole are a conjugate pair. See, the second pole is negative 2 minus plus j5, while the third pole is negative 2 minus j5. So they are in conjugate pairs. Notice that P2 and P3 are in conjugate pairs. Now, to find the inverse Laplace transform of this, right? So, since all the poles are distinct, the function hs can be decomposed into, look at case 1. Now we are applying case 1 here because case 1 applies to the case where all the poles are distinct. So hs would be k1 over s, which is the first pole. Here the first pole is 0, right? So h1, so the first term is k1 over s because the first pole is 0. Now the second pole is minus 2 plus j5, so plus k2 over s plus 2 minus j5, while the third pole is k3 over s plus 2 plus j5. Now you see the signs. If you notice, the signs are reversed. See, the second pole P2 has the real part of negative 2, right? But our convention is s minus p, so we have to multiply negative sign to the negative sign of 2. That's why we got plus 2 here. Okay, please take a note of it. And now, the first one is easy. All right, the first one is easy. We can find k1 right away. Okay, K1 is S times HS, and then plug in S equal to P1, which is 0. Okay, and then once we multiply this guy by S, right, we are practically eliminating the S factor here, right? So we get S plus 1 over S squared plus 4S plus 29. So S plus 1 over S squared plus 4S plus 29. Right? Oh, I noticed that my face is not moving. So let me, sorry. All right. Okay. Now, S is equal to 0 here. So the first, the coefficient K1 is 1 over 29. Now, as for these two terms, okay, we could combine them first, right? Now let's combine these two terms are not easy, more involved than the first one. Now, for the two terms, the last two terms, the other two terms. Now let's look at something. Okay, let's look at K2 and K3. K2 is S plus 2 minus J5, okay, times HS, and then plug in S is equal to minus 2 plus J5, which is the second pole. Okay, that's a second term. So when we do that, we have S plus 1 over, oops, sorry, S times S plus 2 plus J5, and then plug in S equal to minus 2 plus J5. Now, let me tell you that actually we don't really need to do this, okay? But I would like to show you something. I would like to show you that in the end, K2 and K3 are conjugate pairs, okay? Actually, we don't have to do all this, all right? Just want to show you that K2 and K3 are conjugate pairs. And if we had known that K2 and K3 were conjugate pair, then we would have done this thing differently, okay? And it would be a lot easier than this. But this is just for illustration. And if we plug in S equal to this into this guy, we're going to get minus 1 plus J5 as the numerator, while the denominator is minus 2 plus J5 times J10. Oops, sorry. Times J10. Okay, and that would be minus 1 plus J5 over minus 50 minus J20. Okay, and as for K3, we have S plus 2 plus J5 times HS. No, because K3 corresponds to S plus 2 plus J5. So we have to multiply this guy to HS. So we're multiplying it to HS, and then we plug in the pole, which is the third pole, and that is minus 2 minus J5 into the result. And then we have S plus 1 over S times S plus 2 minus J5. Now the reason that I have S plus 2 minus J5 is because we've already, because I multiplied hs by this guy, right? So this guy will cancel this term in the denominator, leaving us only with this term. And then we plug in is equal to -2 minus j5. And then as for the numerator, we have -1 minus j5. And for the denominator, we have -2 minus j5 times minus j10. Okay, and we have -1 minus j5 over minus 50, and then minus and plus j20. Now, look closely at these two terms here. Okay, look closely at this. What do you see? Okay, they are pretty similar, right? They're pretty similar, and if you use calculator, if you use your calculator, you will find that these two numbers are complex conjugate of each other. Okay, they are complex conjugate of each other. From the values. So here we see that K2 and K3 are conjugate pairs. Okay, so the first equation here, let me copy it down, could have been written as, bear with me for a second. So once we know that K2 and K3 are conjugate pairs, we could have written the first equation by replacing K3 with K2 conjugate, right? So K2 conjugate going here. Okay, right? Because K3 is K2 conjugate, right? Star being a conjugate symbol. K2 star means K2 conjugate, the conjugate K2. Okay, so let's do this again. Let's add these terms up again. Okay, once we do that, we have a K2 plus K2 star. And the first term is S, right? Now, we have K2 plus K2 star times 2, okay, and plus 5 JK2 minus JK2 star. Okay. Now, over S plus 2 squared plus 5 squared. Now, let's look at the first term. If you add two complex conjugate together, what are you going to get? So now K2 plus K2 star, what is it? If you add two complex conjugate together, you're going to get twice the real part of it, right? You're going to get twice the real part of it because the imaginary parts will cancel out. Okay, so you're going to get 2 times the real part of K2, right? Now, what about this guy? So these two terms are real numbers. Okay, these two terms are real numbers. What about the last term? J K2 minus K2 star. Now, if we subtract two complex conjugate together, what are we going to get? We're going to get something J2 times J, the imaginary part of K2, right? So we're going to get J times J2 times the imaginary part of K2. Can you see? For example, if K2 is equal to 2 plus J3, right? And K2 star would have to be equal to 2 minus J3, okay? Then if you add them, right? If you add them, the J3 will be gone. The J3 will be gone if you add them. You'll be left with twice the real part, which is 4. So it's this guy. But if you subtract them, if you subtract K2 conjugate from K2, then the 2 will be gone, and you'll be left with 6J, right? Which is this guy. Okay, if you subtract them, you get this guy, right? You get this guy. 6J, which is 6J. Now, because we have this, because we have to multiply it also with J, right? So J times J we know is equal to -1. So that is equal to, that is equal to -2 times the imaginary part of K2. And that is this term. That is the last term. So you see that all of the three terms here are real numbers. So we see that the first coefficient, which is K2 plus K2 star, and the last coefficient, which is JK2 minus JK2 star, are all real numbers. So they are all real numbers. Now, based on this information, we could have written this guy into an even easier form, like this. So knowing this, we can write HS in the following form. Okay, and here. Look here. Because we know that if we combine these two, right? If you combine these two, the numerator will be of this form. Okay, it will be a real number, a real constant times s plus another real number, right? I'm gonna say it again. If we add these two last terms here, the result would have the numerator being one real number, a real number times s plus another real number. See, a real number times s plus another real number. So I could write these two last terms as as plus b, right? Where a and b are real numbers, divided by s plus 2 squared plus 5 squared. Okay. Now, we have to determine the value s. So what is the value s here? So So to determine the values A and B here, so this is the last step, right? Is to determine the values A and B. We could plug in the h here into the left hand side and subtract it by k1 over s, right? So as plus b divided by s plus 2 squared plus 5 squared is equal to hs minus k1 over s, right? Actually, we know already actually that a is equal to the two real part of k2, right? This is a. But we don't want to find k2, right? We don't want to deal with complex numbers. So we want to find a and b differently. So that's why I have this term. And then I plug in hs as where is my sh? Here. Okay, I'm gonna plug in hs here. Here. This is my hs. Okay, and we know that k1 is 1 over 29. Right? We know that k1 is 1 over 29. So we have that. And then I add them together. I add these two terms together. So when I add them, I'll have s times s plus 4s plus 29. Okay, and this will be s plus 1 and minus 1 over 29 times s squared plus 4s plus 29. Now you see where I'm going, right? How come I don't? Hmm. Okay. So I have s plus 1 minus s squared over 29 minus 4s over 29 and minus 1 divided by s times s squared plus 4s plus 29 in the denominator. And you see the factor ones cancel. We cancel out the factor 1 here. So we're left with minus s squared, minus 1 over 29 s squared minus 4 over 29s. Well, actually we have plus 25 over 4 is over s times s squared plus 4s plus 29. Okay, now you see where I'm going, right? So at this point, we know that the denominator are the same, right? They have the same denominator. This guy. But I could cancel s out. Right? Let me do that. I could cancel s out here. S is gone, right? So the numerator doesn't have the s, and one of the s is gone in the denominator. So I have this, right? I have this. You see, the denominators are the same, and because the denominators are the same, the numerators have to be the same as well, right? So now I can compare the coefficients, and right away that I can see right away that A is equal to 1 minus 1 over 29 and B is equal to 25 over 4. Okay? So you see that A is minus 1 over 29 and B is 25 over 4. Okay? And there you have it. And so the last ingredients have been found. So I have H is equal to 1 over 29, which is K1 over S, and plus minus 1 over 29 S plus 25 over 4 over S plus 2 squared plus 5 squared. Okay. Now, to find the inverse of Laplace transform, let's not forget that we are actually trying to find the inverse of Laplace transform. The inverse of Laplace transform, the first term is easy, and that is u, right? That corresponds to u. Now, as for the second term, do you recognize something? We recall that e to the negative at cosine bt ut, right, has the Laplace transform pair of, this is from the table, s plus a over s plus a squared plus b squared. Now you see the resemblance of the form. You see they are very similar in form, right? So a is 2, right? A is 2 and b is 5. But then I have to do something with the numerator to make them in the same form, because what I want is I want the numerator to be s plus a. I want the numerator here to be s plus 2. But now it is not s plus 2, so I have to do something, right? I have to do something. What can I do? Now, oops, sorry. Now notice that minus 1 over 29s plus 25 over 4, okay, that is equal to minus 1 over 29 times s minus 29 times 25 over 4. Right? I took the minus 1 over 29 out. The goal here is I have to make it as s plus 2. I want it to be s plus 2, right? So I can do further, okay, to have s plus 2 as the I can plug in plus 2 there, but when I plug in plus 2, I have to minus 2 in the end, right? Otherwise, they would be equal. So I have minus 25 times 24, 25 times 29 over 4, and minus 2. Okay, so I have minus 1 over 29 times s plus 2, and then plus 1 over 29 times, I have to use my calculator, 29 times 25, 29 times 25 plus 8, that is 733 over 4. That is 116. right? So HS becomes 1 over 29 over S, right? And then minus 1 over 29 S plus 2 over S plus 2 squared plus 5 squared, right? And the last one is plus 733 over 116. I hope my numbers are correct. Over S plus 2 squared plus 5 squared. Now we're almost there because you see the second term, we can recognize the second term now. Right? The second term is there. It's right there. I have A here. Now I have A here, right? So I can take the inverse Laplace transform of the second term to get e to the negative 2 cosine 5t ut. Now, what about the last term? What can we do about the last term? As for the last term, I again look at the table and find that e to the negative t and sine of bt, right? Ut as the Laplace transform as b over a plus a squared plus b squared. So we see the resemblance between the last term here and the Laplace transform of sine. But I have to make the numerator equal to 5, right? I have to make it equal to 5 because this is 5 squared, right? So this has to be 5. So I have to multiply it by 5 and divide by 5 at the numerator. So here, the last term, I can rewrite it as 733 divided by 116 times 5, right? And times 5 over S plus 2 squared plus 5 squared. Okay, and now we see that they are the same. Okay, we see that they are the same except for this constant, multiplying constant. So once again, we have all the ingredients to take the inverse Laplace transform. So plugging in all this, I have HS equal to 1 over 29 over S minus 1 over 29 times S plus 2 divided by S plus 2 squared plus 5 squared. And the last term is 733 divided by 580 times 5 over S plus 2 squared plus 5 squared. Okay? And then the last step would be easiest step because we have put everything into the form that we could take the inverse Laplace transform. Now the first term corresponds to 1 over 29 ut, right? If you take the inverse Laplace transform, the first term will be 1 over 29 ut. And the second term, this guy here is e to the negative 2t, and then cosine of 5t, right? ut. Okay, and the last term is e to the negative 2t and then sine of 5t ut. Okay? Are you with me? I hope you are. If you look at me doing this, you might think it's a little complicated. It's not a little, it's too complicated. But if you do it yourself, if you do it by yourself, then you see that it's not that hard at all. Okay, it flows. You're trying to arrange the things into the form that you can look at the table. That's the bottom line. Okay, but you have to be able to manipulate the algebra to make it into the form that is in the table for you to look up to. So putting them all together, you have 1 over 29 minus 1 over 29 e to the negative t, e to the negative 2t. Actually, I want to do this. Plus e to the negative 2t, right? And the inside is minus 1 over 29 cosine of 5t and plus 733 over 580. My numbers may not be correct, okay? You have to check it again. Then a sine of 5t and then ut. It's not over yet. Let me do the last step to make it the best answer. Now let's look at these two terms. What can we do about these two terms? We can put them into just one cosinusoidal, right? Now, look here, look carefully. I'm drawing a triangle. I'm drawing a right triangle, okay? And then I have this as 1 over 29. And I have this as 377 over 580. Okay, so I can do the Pythagoras to get something here, right? Let's call it A. So A is square root of 1 over 29 squared plus 733 over 580 squared, right? This is A. Okay, so let's not try to find the numbers there, right? Let's call it an A. And this is theta. So once I draw this triangle, these two will be. I could take A out, right? I could take A out. So these two guys, when we add them together, it would be equal to I can take A out, right? When I take A out, I have minus 1 over 29A cosine 5t, okay, and plus 733 over 580A and sine 5t, right? I have this. I hope you guys are still with me. This is nothing at all. I just took A out of the parentheses. When I took an A out, I have to divide A back in to make them equal. Now, if you look at this triangle and you look at this value, what do you see? What is 1 over 29 over A? This is the cosine theta, right? This is cosine theta. Do you see? You see it's a cosine theta. What about this guy? 733 over 580A. That is the sine theta, right? Sine theta. So I have equal to A minus A, right? Minus A. Then cosine of 5t times cosine theta minus sine of 5t times sine theta. Now, do you recognize this? Do you recognize this? What is it equal to? This is a trigonometric identity, right? And we recognize it as cosine of 5t plus theta, right? This is cosine 5t plus theta, where theta is what? Theta is arctangent of 733 over 580 divided by 1 over 29. Okay? And I could use my calculator to get theta, which is arctangent of
or 733 times 29 divided by 580. I got 88, about 88.4 degrees. Theta is about 88.4 degrees. Okay? So I have these two guys equal to minus A times cosine of 5t plus 88.4 degrees. Now let's calculate A. Let's calculate A. 1 over 29 squared plus 733 divided by 580 squared. And then take the square root of it. I have A equal to 1.26. Now, so the last two terms, this guy here, okay, this guy here is equal to 1.26 cosine 5t plus 88.4. I can plug it into my equation. So I have the last step is equal to 1 over 29 and minus 1.26 e to the negative 2t cosine of 5t plus 88.4 degrees, and all multiplied by ut. That's it. This is the answer we're looking for. Barring any mistake I might have done in finding the numbers, the constants, except other than that, it should be this answer. I hope to be able to finish this chapter today, but apparently not. This example is longer than I expected. Okay, let's do another one. Let's do another one. Then this time I'll try to make it shorter. Okay, let's try to make it a shorter version. I intentionally made this example very long because I wanted to show you all the details. Okay, but once I've shown you all the details, I think next time in the next example I'll skip some of the details for you to work out. All right, I'm gonna state right away without going into the details. Now let's look at the last one, the next example, which has complex poles as well. The next example will be taken from my the handout I just uploaded yesterday. So let's look at another one. Again, if you have any question, please don't hesitate to raise your hand. Example. Now I'm trying to make this one very slow. Okay, so we are given the transfer function hs equal to 2s plus 1 over s squared plus 6s plus 25. Now tell me, how can you find the poles? If I give you this function, can you find me the pole? Can you give me the pole? Different person have different methods in finding the poles, right? Some of you may use the formula. There's a formula, minus b plus minus square root b squared minus 4ac divided by 2a, right? That's another formula. Or you could do some perfect square to find the pole. So I'm gonna give you just 1 minute to find the poles. Can you find the poles? The poles. Let's find the pole. So what do you get for the poles? There are two poles, right? And they are both complex poles, right? The first one is 3 plus J4, right? And the second is 3 minus J4. They are complex conjugates of each other. So this is equal to 2s plus 1 divided by s plus 3 squared plus 4 squared, right? Plus 4 squared. So you see they are complex poles. So complex poles P1 is equal to 3, actually minus 3 plus J4, and P2 is equal to minus 3 minus J4, right? Two complex conjugate poles. Now we're trying to arrange this function into the forms that we can look at the table, right? And we have to recall that e to the negative at cosine of bt, cosine of bt ut corresponds to s plus a divided by s plus a squared plus b squared. On the other hand, e to negative at sine of bt ut corresponds to b over s plus a squared plus b squared. So we know that we have to arrange that 2s plus 1 into some of this. Now, so hs, let's try to do this. Now we know that a is equal to minus 3. I'm sorry, a is equal to 3, right? A now is equal to 3. So we'll have to try to make the numerator in the form of s plus 3. So we have 2s plus 3, right? See, s plus 3, so I have to write down s plus 3 to make it consistent with the s plus a. But when I write 2s plus 3, I have 6 that I have to eliminate, right? I have to eliminate the 6 there. So I have to minus 6, take a 6 out. So minus 6 and plus 1 divided by s plus 3 squared plus 4 squared. Right? And then I have 2s plus 3 divided, actually, 2s plus 3 divided by s plus 3 squared plus 4 squared. That is my first term. And the second term is minus 5 divided by s plus 3 squared plus 4 squared. Now the first term is ready. Okay, the first term is in this form already. So it is ready to take the inverse Laplace transform, right? Now what about the second term? For the second term, you have to look at the other one here. But it is not ready yet, right? Because this number b squared has to be the same as this number b. But here, this is 4, but this is 5. So we have to do something about it. What can we do? So we want to make it 4, right? So I have to erase the 5 there and replace it with a 4. But once I know when I do this, it is not correct, right? So I have to take the 5 out and divide it by the 4. See? Now they are equal. Now they're the same. Now now it is correct. And here I have made this into the second form. So I can take the inverse Laplace transform of the second term
And so ht is equal to the first term is 2e to the negative 3t cosine of 4t, right? And the second term is minus 5 over 4 e to the negative 3t, a sine of 4t, and then multiply all the way through by ut. We're almost there. And then I can take the e to the negative 3t out, right? So I have e to the negative 3t, and the inside is 2 cosine of 4t minus 5/4 of sine 4t ut. And again, I can write a triangle, a right triangle, okay, where the vertical length here, the height is 5/4, and the width, the horizontal is 2, This is 2. Okay, so I have 2 here, and I have theta, and I can do the Pythagoras again to make this one equal to 4 plus 25 over 16, and that is 4 plus 25 over 16, and then take the square root of it. Oops. I have 2 plus 3, 6. 2 plus 3, 6. Here. Okay. So I have e to the negative 3t. 2 plus 3, 6, e to the negative 3t. And the inside is 2 over 2 plus 3, 6 times cosine of 4t minus 5 over 4 over 2 plus 3, 6 sine of 4t ut. Right? And then I recognize that this is what? This is cosine theta, right? And this is sine theta. Okay? So I can use a trigonometric identity to get it equal to 2.336 e to the negative 3t and cosine of 4t plus theta ut. Now, what is theta? I can find theta by looking at this triangle, right? Where theta is equal to arctangent of 5 over 4 divided by 2. Okay, and using my calculator, I find that arctangent of 1.25. 5 over 4 is 1.25. Divided by 2 is 32 degrees. Exactly 32 degrees. And so I plug it in. I have 2.36 e to the negative 3t cosine of 4t plus 32 degrees ut. And that is the answer. Okay. So you see, in the complex pole case, it's a little bit more complicated than the other two cases. The easiest one is is that all the poles are real numbers and distinct. That's the easiest one. That's the first case. The second case was some poles are repeated and all the poles are real numbers. That's the second easiest one. And this one is some of the poles are complex numbers. This is the most complicated one. And you see, when some poles are complex numbers, the inverse Laplace transform
will be sinusoidal. In other words, it will be oscillating. Okay, but if the poles are real numbers, then the inverse Laplace transform does not contain sinusoidal function and it is not oscillating. So notice when there is a complex pole HT will contain a sinusoidal term. Okay, that is, it oscillates. Now, what is the frequency of the oscillation? The frequency of the oscillation would be the imaginary part of the pole. Imaginary part of the pole, of the complex pole. For example, oh no, the unit is in radians per second. Radians per second. For example, if we look at the last example, look at this example. In this example, the transfer function is given as this. And we find that the poles are complex, right? The poles are complex. Now, if you look at the poles, the imaginary part of the pole is 4. And it is the number 4 here. That is the frequency of the oscillation. 4. So this is the imaginary part of the pole. Now, if you look at the pole again, you see -3 here. So what does it mean here? What does it determine? The -3 here determines the exponent term here. -3 goes here. So if you plot this graph, you'll find that it is a sinusoidal, decayed sinusoidal with decayed amplitude. The oscillation frequency of the sinusoidal is 4, which is the imaginary part of the pole. And the decay factor, how fast it decays, is determined by the real part of the pole. Okay? So -3, which is the real part of the pole, determines how fast it decays, how fast it goes to 0. While the imaginary part of the pole determines the frequency at which it oscillates. So that's how important the poles is. Okay, that's how important poles are. The real part, the real part of the pole determines how fast the amplitude of oscillation will decay. That's what I mean is this. If you plot this, if you plot HT, you'll find that it looks like this. This is the plot of HT.
Okay, and it starts at 0. Now, you see HT oscillates, right? It oscillates. And the period of oscillation, T0, is 2 pi over omega 0. Okay, 2 pi over omega, which is, in this case, omega is 4, right? Omega is 4. So 2 pi over 4. The period of oscillation is 2 pi over 4. Now the decay rate, here, this is, you see, the amplitude decays exponentially. The rate of decay is determined by the factor -3, right? So the larger the A is, the faster it decays. Last example. Given Hs equal to S over S squared plus 2S plus beta. Okay. Given Hs equal to S over S squared plus 2S plus beta. The question is, determine the range of beta for which the impulse response does not oscillate. What is your idea? What is your strategy of doing this? Beta is a real number. Okay, beta is a real number. Sorry, I have to indicate that. Beta is a real number. We want to find for which beta does the impulse response not oscillate. So what do you think? How do we approach this? How do we do this? We have to use the fact that HT will oscillate when there is a complex pole, right? Right? HT oscillates when some of the poles are complex numbers, meaning that imaginary part is not 0. So we know HT will oscillate. Other words, contains sinusoidal function will oscillate if there is at least a complex pole. Okay, so in this case, we don't want it to oscillate, right? So we don't want any complex pole. In this case, we want to find beta such that no poles are complex. Because we don't want it to oscillate, right? Since we don't want to oscillate, the poles cannot be complex numbers. So all the imaginary parts have to be 0, right? So let's find the poles. Now, S squared plus 2S plus beta. Now, how do we find the poles of this? Another way, one way is to write it like this, right? One way is to write it like this.
and beta minus 1 has to be positive, right? So beta has to be. Another way is to use the formula, right? So let's do another way. So let's make it equal to 0, and let's find the root of this. Let's find the roots of this. Now, can you find the root of this? Of course you can, right? So the root is minus 2, right? Plus minus square root of 2 squared minus 4 beta divided by 2, right? Divided by 2, right? Okay. Since so poles here. Since P cannot be complex, since the poles cannot be complex, what do you want? This term has to be greater than 0, right? This term cannot be negative. If the poles, for the poles to not be complex, this term cannot be negative. If this term is a negative number, then P is a complex number, which we don't want. So, since pole P cannot be complex, 2 squared minus 4B has to be greater than or equal to 0. So that means beta has to be less than or equal to 1. That's it. That's the answer. So for this system to not oscillate, for this system to not oscillate, beta has to be less than or equal to 1. Okay, if beta is greater than 1, then system will oscillate. It will contain a sinusoidal term in the impulse response. Okay? All right. Okay, so yeah, see you again on Tuesday. I guess this is the end of it. We are out of time. I hope you find it enjoyable.